Welcome, everyone. Today we are exploring a vital strategy for balancing the costs and benefits of AI-powered business solutions, implementing a model router. Let's get started. Welcome to our first slide on implementing a model router. What exactly is a model router? In modern AI applications, organizations rarely rely on just one model. They use a mix of general-purpose large language models, small language models, and fine-tuned models. The basics involve setting up Azure AI Foundry's model router, which provides a single, unified endpoint that automatically selects the best model for each individual request. Why is this necessary? Because calling a massive LLM for a simple task wastes money and compute. How does it work? It sits between your application and your models, applying routing rules and performance criteria. When you implement this, you eliminate the need for your app to hard-code model selection. For our deep dive, consider the architectural impact. By offering one endpoint for multiple models, you drastically reduce code complexity and simplify application integration across your entire enterprise. This unified approach ensures that every request is handled by the most suitable model without burdening developers. Let us turn our attention to the flowchart on the screen. On the far left, we have the application request. This represents a user query or system trigger. Instead of routing directly to a specific AI model, the request flows into the central node, our model router endpoint. This is the single unified gateway. From this gateway, the diagram branches out to three distinct model types. The top branch leads to a small language model, or SLM. The middle branch routes to a custom fine-tuned model. The bottom branch connects to a general-purpose LLM. This visual beautifully illustrates the core concept. The application only needs to know how to talk to one endpoint, while the router intelligently delegates the workload behind the scenes. By managing the routing centrally, the system ensures that the application remains lightweight, decoupled from the underlying AI infrastructure, and capable of adapting to new models as they are registered into the ecosystem. Moving to slide 2, let's explore why model routing matters from a cost and benefit perspective. What is the primary value proposition? It enables organizations to balance high performance with financial sustainability. The basics of this value are rooted in 4 areas: cost optimization, performance, reliability, and hybrid AI support. Why should we care about cost optimization? Because by using small language models, or SLMs, for simple tasks, you reduce token consumption and only pay for expensive LLMs when complex reasoning is truly needed. How does it improve performance? The router can direct low-latency tasks to faster models or highly specific tasks to domain-specialized models. As a deep dive, consider the hybrid AI strategy. Many organizations operate under a build, buy, or both transformation strategy. A model router seamlessly supports this by combining out-of-the-box foundation models with your own bespoke fine-tuned models, allowing you to maximize the return on your AI investments without locking into a single vendor. Looking at this value breakdown diagram, we see model router value at the top, branching into 4 distinct operational benefits. The first branch, optimize cost, highlights how we can deploy SLMs for simpler tasks, directly reducing token consumption. The second branch, improve performance, shows that we can achieve lower latency by matching the right task to the right model size. The third branch focuses on increased reliability, which we will explore later regarding backup models. The final branch, support hybrid AI, visually demonstrates how foundation models and custom models can coexist in your architecture. As an architect, communicating these 4 pillars to business stakeholders is essential. It proves that AI adoption doesn't mean writing a blank check for the most expensive language model. Instead, it shows a governed, cost-conscious approach that maximizes efficiency while ensuring the system remains incredibly fast, resilient, and perfectly tailored to your business needs. On slide 3, we examine the routing criteria. What exactly does the router use to make its decisions? The router evaluates each request against specific criteria to determine the most suitable destination. The basics involve assessing 2 primary factors, the task type and the complexity. Why is this distinction important? Because a simple text classification shouldn't require the same compute power as deep conversational reasoning. How does it evaluate this? Azure AI Foundry supports rule-based and metadata-based routing. It looks at task types such as summarization, extraction, classification, reasoning, or open conversation. For our deep dive, let's look at the complexity scale. If a task is simple, the router directs it to an SLM. If the task is moderate, such as domain-specific entity extraction, it goes to a fine-tuned model. If the task is complex, it is routed to a powerful LLM. By defining these criteria, you ensure you never over-provision resources for basic business workflows. This flowchart demonstrates the decision-making process based on task complexity. On the left, we begin with an incoming task. This immediately feeds into our central decision gateway labeled complexity. The router acts as a traffic controller here, evaluating the metadata of the prompt. Follow the top path. If the task is evaluated as simple, it is efficiently routed to a small language model, or SLM. The middle path shows that a moderate complexity task is routed to a fine-tuned model, which has been specifically trained for your domain. The bottom path demonstrates that only when a task is deemed complex requiring deep reasoning or extensive context is it sent to the more resource-intensive general-purpose LLM. This diagram makes it easy to perceive how dynamic routing acts as a cost-saving filter, preserving your expensive compute tokens for the workflows that genuinely demand high-tier artificial intelligence. Slide 4 focuses on designing specific routing rules. What are these rules? They are the programmed logic that instructs the router on how to handle traffic. The basics include defining static rules and weighted routing configurations. Why do we need different rule types? Because enterprise needs vary. Sometimes you need rigid, predictable routing, and other times you need dynamic load distribution. How are these applied? Static rules are if-then statements. For example, you can set a rule that says, if task equals classification, use an SLM, or if domain equals finance, use the fine-tuned model. In a deep dive, let's discuss weighted routing. Weighted routing allows you to distribute traffic across multiple models by percentage. This is incredibly useful for A/B testing or executing a gradual rollout of a newly fine-tuned model. By sending 80% of traffic to your stable model and 20% to your experimental one, you can safely evaluate performance without risking the entire production workload. Let's review the architectural patterns for routing rules in this diagram. From the top router rules node, we split into two fundamental strategies. The left branch takes us to static rules. Connected to this is a practical example, if domain equals finance-fine-tuned model. This represents strict, deterministic behavior. Now, follow the right branch to weighted routing. Here, the traffic is intentionally split. We see one path sending 80% traffic to stable V1 model, while the secondary path sends 20% traffic to experimental V2. This visual clearly distinguishes between absolute routing and proportional routing. As a solution architect, you will frequently use the right side of this diagram during the development lifecycle to safely introduce new models into production. It illustrates how we can innovate and iterate on our AI capabilities with zero downtime and minimal risk to the end-user experience. On slide 5, we continue with routing rules, focusing on resiliency through fallback and version-based routing. What is fallback routing? It is a safety mechanism that automatically redirects a request to a backup model if the primary model fails. The basics of version-based routing involve directing traffic to specific iterations of a model. Why are these essential? They directly address the increased reliability benefit we discussed earlier. If an API endpoint experiences an outage or a rate limit is hit, your application shouldn't crash. How do you implement this? You configure the router to detect failure codes and instantly fail over to a designated secondary model. Diving deeper, version-based routing is vital for enterprise governance. You can set a rule to always route to the latest stable version of a model, ensuring your production apps always benefit from the most secure and capable releases, while isolating specific test traffic to experimental versions. This diagram maps out our resiliency and versioning configurations. Starting on the left, an app request enters the system. Let's trace the top pathway first, demonstrating fallback routing. The request is sent to the primary model. However, we see a dashed line indicating a failure or timeout. When this occurs, the router immediately executes a failover to the fallback backup model. This ensures the user still receives an answer without experiencing an error screen. Now, looking at the bottom pathway, we illustrate version-based routing. The request hits a version rule gateway. Based on the configuration, the rule directs the workload strictly to the latest stable version of the model. This flowchart is a powerful representation of enterprise reliability. It proves to business stakeholders that our AI architecture is fault-tolerant and strictly governed, preventing unpredictable outages and maintaining seamless operational continuity. Slide 6 shifts to the actual implementation process, starting with steps 1 and 2. What is the first phase of implementation? It requires defining your overarching routing strategy and registering your models in Azure AI Foundry. The basics dictate that you must choose whether your strategy will be cost-optimized, performance-optimized, accuracy-optimized, or a hybrid approach. Why do we start here? Because solution architects should conduct a routing rule design workshop to identify these business tasks, as rules vary greatly between organizations. How do we move forward? Once the strategy is set, step 2 is to register your models. For our deep dive, recognize that registering models means bringing your diverse AI portfolio under one roof. You will register out-of-the-box foundation models alongside your custom and fine-tuned models. This centralized registry is what allows the router to dynamically select the best asset, transforming a fragmented AI landscape into a unified, accessible catalog. Let's explore the first 2 steps of implementation on this flow diagram. On the left side, we have Step 1, Define Strategy. From here, we see the primary strategic options branching out: cost-optimized, performance-optimized, and accuracy or hybrid. During your design workshops, you will align your business goals to one of these paths. On the right side, the flow transitions into Step 2, Register Models. This node branches into the 2 main categories of models you will connect to the router: foundation models provided by Microsoft or partners, and custom/fine-tuned models developed internally by your data science teams. This visual emphasizes that implementation is a sequential process. You cannot effectively register and route to models until you have explicitly defined the strategic business outcomes you are trying to achieve with your AI investments. Continuing our implementation journey, Slide 7 covers Steps 3 and 4, Configuration and Integration. What happens in these steps? You take the strategy defined in Step 1 and physically configure the routing rules, then integrate the router with your applications. The basics involve setting up the static, weighted, and fallback rules we discussed earlier within the Azure AI Foundry interface. Why is integration Step 4 so critical? Because this is where the business actually realizes the value of the router. How do you integrate it? You point your backend services to the router's single unified endpoint. For a deep dive into integration, the model router doesn't just connect to simple web apps. You will integrate this endpoint into sophisticated AI agents, Copilot extensions, and multi-agent systems. By pointing these complex systems at the router instead of hard-coding specific LLMs, you future-proof your architecture, allowing you to swap or upgrade models behind the scenes without rewriting application code. This flowchart visualizes the critical integration phase of our deployment. We begin at the top with Step 3, Configure Rules. This leads directly into the application of our static, weighted, fallback rules inside Azure AI Foundry. Once those rules are firmly established, the flow moves downward into Step 4, Integrate with Apps. From this integration node, we branch out to show the vast ecosystem of consumers that can leverage the router. We see branches for AI agents, Copilot extensions, and complex multi-agent systems. What this diagram elegantly illustrates is the decoupling of logic. The applications at the bottom do not need to possess routing intelligence or contain complex model selection code. They simply query the router, and the router handles the heavy lifting. This centralized architecture drastically simplifies ongoing maintenance and scaling for your development teams. Our final slide addresses Step 5, Monitoring and Optimization, along with centralized governance. What is this final step? It is the continuous operational lifecycle of the router. The basics require you to monitor metrics like latency, cost, accuracy, and model usage distribution. Why is this continuous loop mandatory? Because AI workloads fluctuate, and routing rules designed on day 1 may need adjustment by day 30 to remain cost-effective. How do you govern this? The router natively provides centralized governance features, including versioning, usage analytics, and safety controls. Taking a deep dive, solution architects must use this telemetry to identify inefficiencies. If you notice a fine-tuned model is experiencing high latency or an SLM is failing accuracy checks and triggering human escalations, you must tune your routing rules. This creates a closed-loop system where data drives continuous improvement, ensuring your AI strategy constantly optimizes the balance between cost and business benefits. Our final diagram depicts the continuous optimization loop that governs our model router in production. We start on the left with Deploy Router. As soon as it is live, the flow moves to Monitor Telemetry, where the system actively tracks cost, latency, and accuracy. This data feeds into the Identify Inefficiencies node. Here, architects analyze the telemetry to spot bottlenecks or cost overruns. The insights gained lead us to tune routing rules, where we adjust our static or weighted parameters. Notice how the arrow from tune routing rules loops all the way back to the beginning. This circular diagram reinforces a vital lesson for solution architects. Deploying an AI model router is not a one-time event. It is an ongoing, iterative practice. By continuously monitoring and refining the system, you guarantee that your AI solutions remain highly performant, secure, and financially viable over their entire lifecycle.